Good morning and welcome to class 30.5. Today is our catch-up day on our tests for convergence. We're on page 46 in the packet. Let's jump in at the top. Today is all about practicing with our new tests for convergence of infinite series. Let's review the tests for convergence of infinite series and strategy guide, which is pages 1 and 2 of this big packet. So let's take a look back here. So on the very first page, the test for convergence of infinite series, let's just look at one row to get a sense of what this table is telling us. How about, for example, the row with the ratio test in it? Oops, not that one, but this one right here. So what are we looking for to use the ratio test? Well, it says you use for a series which contains factorials or powers. So that's what we're looking for. If you see a series with factorials or powers, the ratio test is a good tool to try. If this particular limit is less than 1, that is the limit of the absolute value of the next term over the current term. If that fraction goes to any number less than 1, converges to some number less than 1, then the series converges, the original series. But if that limit is bigger than 1 or is infinity, then the series diverges. And then finally, if it happens that this limit is equal to the dreaded number 1, then the test tells you nothing. It doesn't say the series converges. It doesn't say the series diverges. It doesn't tell us anything. We just need to use a different test because the ratio test failed. All right, so here's our summary of like how all of the different tests work. And on the back of this page is basically a flow chart. It's called the strategy guide, testing infinite series for convergence. And this is our best effort at trying to give you a step-by-step process, a decision process to decide, which of the many different infinite series tests might be the appropriate ones to use, and in which order should you think about using them. So we're not going to read everything on this page, but just a rough sense of what the questions are and what order should we ask them. So first, is the series a p-series, which means it's 1 over n to some number, or is it a geometric series, which looks like a number times a number to the n? If so, then it's really easy. It's just the p-series test or the geometric series test. If it's neither of those series, then ask our next question. Did the terms approach anything other than 0? If they do not approach 0, the series diverges. That is the nth term test, and you are done. If the first two questions we asked didn't get us anywhere, then maybe you get to question 3. Are some terms negative? If so, then maybe the alternating series test, maybe the absolute convergence test. Number 4, does the series involve factorials or exponential expressions? So we just saw those on the back of this page. If so, you use the ratio test. Number 5, is the series similar to a p-series or a geometric series? Similar, not exactly equal to, but similar. Then you can try the direct comparison test, which I never use, or the limit comparison test, which I use every time I'm thinking about comparing. And then last but not least, have none of the above things worked, then maybe, let me try the integral test. Otherwise, maybe we just missed something and it should have been up above, an easier technique. The integral test is intentionally placed last here. It is the hardest test that we have, and that's why we put it off until the end. Okay, so as you're working through homework and practice problems and all that jazz, just maybe have that page in front of you as a reference guide. Okay, so let's take a look at number 2 here. It says, let's discuss what tests might be appropriate to try for the following series. We're not going to write out all the details of these tests, but just get a sense of like what makes each test work. Which series scream this test over this other test. Okay, part A, summation 3 to the n plus 5 over 4 to the n. So my first thought is that this plus 5 right here doesn't really make much of a difference, right? 3 to the n is going to be way bigger than this plus 5. So what if I just ignore that? And we'll have to like formally do something to allow us to ignore it. You don't get to just ignore it, but let's see what happens. So 3 to the n over 4 to the n, that's actually a geometric series. We're going to write that out in just a second. But even though that thing with the plus 5 crossed off is a convergent geometric series, adding 5 makes our series bigger than something which converges. And that's unfortunate, right? Like maybe our series also converges, but maybe that plus 5 makes it just big enough that it actually gets to infinity. So we can't, unfortunately, just ignore the plus 5, even though it's dominated by the 3 to the n. Okay, what can we do? Well, we can actually split this into two separate series. So here we go. This is a single denominator. And so we can put that denominator inside of two fractions. And so why is that better? Well, at the very least, we can consider these two series separately, and they're both simpler than the original series. We're going to now start rewriting so that these series look like forms of series that we've seen before. So the first one, for example, is 3 over 4 to the n. And that's a geometric series. The second one is also a geometric series. I'm going to write it as 5 times 1 over 4 to the n. And now that I've got them written in geometric series form, and I recognize they have the geometric series form, then I can use the geometric series test. And in both cases, the ratio is less than 1, right? 3/4 on the one hand, or 1/4 on the other hand. And in each case, the ratio is less than 1, so the series converges, and that's the end of the game. Again, not writing out all the details, probably good practice for you to write out all the details, but right here we're just looking for the right path that we should take. Okay, next one, summation, 3n squared plus 2n over 7n cubed plus n squared plus 1. Okay, so in this case, polynomial over polynomial, that says to me we should be doing a limit comparison test. So first we're going to figure out what we think this series behaves like. So upstairs, everything other than the leading term is going to be inconsequential. So the leading term upstairs is 3n squared. Same deal downstairs, only the 7n cubed is going to matter, which means that temporarily we're going to ignore the plus 2n, and we're going to ignore this plus n squared plus 1, and we're going to look at what's left. And what's left has some n's that I can cancel. And if I cancel two n's from top and bottom, then we get 3 over 7n. And so that is what we're going to compare to. Summation 3 over 7n. And in fact, when I do the limit comparison test, I actually ignore even the 3 and the 7. And so I'm going to cross that off and say, let's just compare to 1 over the n. The only thing that matters is the power on that n. The 3 and the 7 are going to be inconsequential. So we'll just compare to 1 over n. And let's go ahead and start our limit comparison test. And so remember, that means you take a limit as n goes to infinity, absolute value. So right after I said absolute value, I thought I remembered that the limit comparison test is only good for a series with positive terms in it. And I looked on our reference sheet, and that's right. So we actually don't need the absolute value for limit comparison test. What we need is to compare the general term of one series to the general term of the other. So arbitrarily, I will choose to put this one first, or on top, I should say. And then divided by the other series, the series that we pulled out of a hat, 1 over n. And we need to figure out what this limit is. The options are not 0, not infinity, or 0, infinity. And so we just have to figure out which this is. So let's see, limit n goes to infinity. So I'm going to flip that 1 over n upside down and bring it upstairs. So it becomes times an n over 1. And then let's distribute that n on top. So I get 3n cubed plus 2n squared over, and then copy the denominator. And now we get a limit that we can calculate. And so this is an easy pre-calculus limit idea here. We're just comparing the highest power top and bottom. In this case, it's a tie. Power is 3 for both of them. And when it's a tie, that means that the limit, the final answer, is just the quotient of the coefficients, the leading coefficients. So 3/7 is our limit here. And that 3/7 is not 0 and not infinity. And so we'll leave it to you to conclude, like what else can you say about our series? Don't forget, you do have to talk about the simpler series we're comparing to. summation of 1 over n is a harmonic series, we know whether that one converges or diverges. And then the limit comparison test says because our final limit was not 0 and not infinity, this series behaves exactly the same as that one. So once you figured out what this one does, converges or diverges, this one over here does the same. Okay, part C, summation n minus 1 factorial divided by 5 to the n. So both the factorial and the exponent scream ratio test. So that is the test that we're going to use here. We'll just get it started. So the ratio test says you're going to take a limit as n goes to infinity, and we're doing absolute value of the next term. So all of the n's become n plus 1s divided by the current term, but I'm going to go ahead and save some time and multiply by the reciprocal of the current term. Okay, and then let's clean this up here. Limit n goes to infinity. So the top left piece, the plus 1 and minus 1 cancel. So that just leaves me with an n, and it's in a factorial. And then let's go ahead and look at the 5s. So there is one more 5 on the bottom than there is on the top. So that means all of the 5s on top go away, and there's just a single 5 left on the bottom. So that's what we're going to write in our simplified version over here. Single 5 in the bottom. All the 5s on top go away, so I'll put a 1 up there, and then I'll copy this n minus 1 factorial. And then we know how factorials cancel. In this case, the n factorial is bigger, one term bigger than the n minus 1 factorial. So all that's left when I cancel those factorials is going to be a single n on the top. So let's write that. Limit n goes to infinity. So we've got a single n upstairs and a single 5 downstairs. I'm not going to write the absolute value anymore because all of the everything here is positive. And what is this limit equal to? Well, this limit is equal to infinity. And so if that limit had been something less than 1, then we would say by the ratio test that the series converges. In this case, though, the limit is greater than 1, clearly. And so by the ratio test, our original series diverges. Remember, if we had gotten not less than 1 or greater than 1, but exactly 1, then the ratio test would be inconclusive and we would need to use another test. If, for example, back here on part B, we had tried the ratio test, we would have gotten a limit equal to 1, which means the ratio test doesn't tell you anything. Next page, part D, negative 1 to the n over n squared minus 1. We're actually going to fix this here and make this n equals 2. That's what it should have been. Okay, so what do we see here? Well, that negative 1 to the n is a telltale alternating series, and so we're going to try the alternating series test because of the alternating nature of this series. Okay, and so the alternating series test involves checking 3 facts. You need the terms to alternate, and you need the terms after you handle the fact that it's alternating. Like ignoring the alternating nature but treating all the terms as positive, you need the terms to form a decreasing sequence. And you also need the limit to be 0, the limit of the terms to be 0. And so we're not going to do the details here, but I will leave it to you to, in fact, show that, yes, all 3 of those things are true. And the alternating series test, therefore, tells you that this series will converge. That's always the conclusion when those 3 blue things are true. Okay, part E, determine whether the series is absolutely convergent, conditionally convergent, or divergent. Okay, let's try this one. So again, we've got an alternating series thing happening here. And so task 1 is to just use the alternating series test on this series in its original form. And I'll just say, check the 3 conditions that we just wrote down above. And in this case, you will again find that all 3 of them are true, which means that this original series converges. So we'll just write that, -1 to the n over n to the 1/2 converges by the alternating series test. But we have to go farther with this one because we need to know, is this series absolutely convergent or only conditionally convergent? And what that means is that we consider a new series, which is the same as the old series, but with absolute value around the whole thing. And the absolute value has a really simple impact on this one. -1 to the n, well, that's the thing that goes between +1 and -1, just back and forth. But the nice thing is the absolute value of both +1 and -1 is plain old 1. And n to the half is always positive. So absolute value just gets rid of that -1 to the n. It just makes it a straight up 1 every time. And so now we have a brand new series, summation 1 over n to the half. We need to decide if the series converges or diverges, but hey, it's a p-series, and so it's really easy. In this case, p is equal to 1/2, and remember our cutoff for p-series converging is 1. I guess I'll say it's less than or equal to 1. And so that means that we're on the divergent side of the cutoff, and so that means that the summation of 1 over n to the half diverges. And that's the p-series test. And armed with our two facts, the green original series converged, but the blue series diverged. That means that we are ready now to say whether the original series is absolutely convergent or only conditionally convergent. In this case, it is conditional. So we'll copy the original series, no absolute value, and write our conclusion. This one converges conditionally. Okay, and then finally here, part F. Oh, not finally, two left. 1 over n times sine of n squared. Okay, so the sine of n squared, that's a really complicating thing, but for sure, if we have sine of n, we're going to have to make use of the fact that that series is always between -1 and 1. And so if I square it, that gets rid of the negative parts, but it still keeps the upper bound of 1. So sine of n, the whole thing squared, is always between 0 and 1. So what does that mean? So let's compare, let's just look at the denominator. Sine of n squared times n. How does that compare to plain old n? We're going to put either a less than symbol or a greater than symbol. We know that this thing right here is trapped between 0 and 1. And multiplying a positive number by something between 0 and 1 makes that number smaller. And so that means that the inequality is this way. And then building the fraction in the original series, 1 over both of these things. Flips the direction of the inequality. So we now have a greater than symbol. And so that leads us to consider the summation of 1 over n. That's this one right here. And we know that that is the harmonic series, which diverges. And that means that the series that we have is greater than something which diverges. And I mentioned earlier that I never use the direct comparison test. I always use the limit comparison test. Well, here is the one case where I turn into a liar. We're going to use the direct comparison test. CT, I guess DCT, direct comparison test. Because our series is greater than something which diverges, therefore our series also diverges. Okay, and then finally G. N squared over n squared plus 1. Do the terms of the series approach 0? Well, let's take a look at this thing. So we've got limit n goes to infinity of just the terms. And I know there are a lot of limits in our series test, but this is not comparing this series to another series, and this is not taking the next term of this series and dividing it by the current term of this series for the ratio test. This is just straight up look at the terms of the series. And in this case, again, it's our pre-calc limit, right? Where the power on top and bottom is the same. We get to ignore everything except for the leading terms. And so that means that the limit is just the quotient of coefficients. I will put a 1 here and a 1 here and say, therefore, the limit is just the top one divided by the bottom one, which is plain old 1. So that means that the terms of the series approach 1, which is not equal to 0. And that means that basically the series involves adding infinitely many numbers, like many of which are basically equal to 1, really close to 1 anyway. And if you add infinitely many things that are basically equal to 1, for sure you're going to get infinity. And so this series diverges, and that is the nth term test. Or divergence. Okay, so I think we took care of all of the tests on this page, except we didn't see an integral test. Like I mentioned, the integral test is the hardest one. It is the last thing in our flowchart decision tree for a reason. And so I guess I would say if there were another series in front of me and I went through my whole flowchart and none of the things that we did on these 2 pages worked, I would consider, if it wasn't too painful, trying to use the integral test. And that means trying to find an antiderivative of the function that defines this series. But that is a last-ditched bailout effort. It is certainly not the first thing to try. Okay, so the activities on the next page. The activity is actually to start your homework assignment. So go ahead and read that on the next page, and I will walk around.